Hello everyone, this is Dr. Zach. For today's lesson preview, you are given a differential equation and an initial value. Use Euler's method and 2 steps to approximate y at 0.5. Please do not use a calculator. For question B, I want you to determine y and then compare your estimate to y at 0.5. So go ahead and get that lesson preview started. Okay, so for question A, did you remember to make a table with your values and make a final statement as to what y at 0.5 is going to be approximately equal to? And for question B, did you remember to use separation of variables? And then once you integrate, don't forget your plus c, and after you have it in the form y equals c e to the negative cosine t, you're going to use 0, 1/2 in order to find that c value. Afterwards, what is y at 1/2 and how does that compare to the value that you have in your table? For today's lesson, we're going to use structures to help us determine antiderivatives. So last class, we said that if your problem is in a logistic form, your differential equation shows you a logistic equation, then you should just immediately write down that what y is equal to. Now, at this point, we're going to look specifically at first-order linear differential equations. And those equations must be in the form dy over dx plus some function of x times y equals another function of x. So p and q are continuous functions of x. This is called a first-order linear differential equation in standard form. Please note that p of x and q of x could be constant, and if q of x equals 0, then this is a special linear differential equations. It's called homogeneous, and it's the homogeneous equations that you're able to solve using separation of variables. So we have already worked on the homogeneous equation. That would be question A in your lesson preview. The first thing we'd like to know is whether these equations are actually first-order differential equations. So look at the structure. Do we have, for question A, dy dx to start with? Yes. All right. Do we have some function that is a function of x multiplied by y? Yes, we do. But the 3 is on the wrong side. So if we were to rewrite this in standard form, y prime minus e to the x y is going to be equal to -3. So that problem is definitely a first-order linear differential equation. It is not homogeneous, so I'm actually not able to use separation of variables to solve it, but it is in standard form now. Now when we look at question B, all right, small changes occurred with question B. I still have a y prime, that's good. Here is a function with respect to x multiplied by y. That's good. And in this case, remember that q of x is equal to 0. So is this a first-order linear differential equation? Yes, and it's actually a special one. This one is homogeneous. And in order to solve it, you would need to use separation of variables. And we can only do that when we have homogeneous differential equations. Now, looking at question C. Notice this says y double prime. So linear, first power. This one is a second derivative. So is this a linear first-order differential equation? And I'm hoping that you said no, because it's got y double prime. All right, looking at question D. Again, I have y prime. Check. I have minus e to the x, so that would be my p of x in this problem. P of x is negative e to the x. And then we also can see that we have q of x in the problem, and that one is x squared. So this problem is first-order linear differential equation. It is not homogeneous, and I cannot use separation of variables to solve it. Question E. All right, so looking at E, this one kind of looks like it's a logistic equation, but it's not in the standard form of my first-order linear differentials. Let's change this around. dy dt is equal to km minus k times y. Rearrange things a little bit. We get dy dt minus, becomes a positive, ky is equal to km. All right, so I've rearranged the problem. Is k, could I rewrite that as p of x? The answer is yes. Remember, we can have constants multiplied by that y value. And what about q of x? Once again, we have constants, and the constant is k times m. So yes, this is a first-order linear differential equation. However, I cannot use separation of variables to solve it. Now, here's some good news. We can actually solve first-order linear differential equations, even if they are not homogeneous. And how we're going to do it, so we're going to find something called an integrating factor. Now, you know that a factor is something that you multiply across a function. So if we very cleverly choose the factor e raised to the integral p of x dx and multiply that throughout this function, we're going to be able to solve our function. Let's see if this is true. All right, so let's see here. U of x is going to be equal to e, the integral of p of x dx. If I take that and multiply through, we have y prime times e integral p of x dx plus p of x times y times the integral, e integral p of x dx. So notice I'm just multiplying through. That's going to be equal to qx multiplied through by e, the integral p of x dx. All right, so notice again, what did I do? I multiplied through by this expression for each part of my problem. Now, this is why this problem is so cool. Look at this. I have y prime. I have y. I have e to the integral p of x dx. And then I have p of x with the integral e integral p of x dx. Now, if you are feeling super clever today, I'm hoping that you recognize this as part of your product rule. D dx of what values? We'll have y and e to the integral p of x dx. Do you see that this entire expression on the left-hand side is part of a product rule? Think about that. And on the right-hand side, we have q of x times e to the integral p of x dx. Now, if we integrate both sides, just multiply by dx, so then we'll have ye to the integral p of x dx so we're integrating, but then we need a dx over here. That's going to be equal to the integral q of x e integral p of x dx with dx here. And since we've integrated that left-hand side, I'm going to throw a plus c on my right-hand side. Okay, so that is how we're going to use an integrating factor. We are going to finally undo the product rule. Did you notice that after all this time in calculus, you have never deconstructed the product rule to get it back to integration? And that is how exciting the first-order linear differential equation can become. Let's check out example 2. Do you agree that our given equation is a first-order linear differential equation? That x is in the wrong spot. Let's see what happens. We will get, when we rewrite the problem, dy over dx is equal to minus 1 over xy has to be equal to 1. We recognize that p of x is going to be equal to negative 1 over x, and q of x is going to be equal to 1. The integrating factor, let's find that. So our integrating factor is going to be equal to e, the integral of our p of x dx. Okay, so we should integrate this, and we get e negative natural log of x. Now there's a plus c, but we don't write it at this point when we find our integrating factor. This can be simplified though. E to the natural log of 1 over x, which simplifies some more. That is just 1 over x. So the integrating factor is 1 over x. So we're going to take that and multiply it by each part of our expression. So we will have 1 over x dy dx minus 1 over x times the original 1 over x. Y is equal to 1 over x. However, I'm hoping that you realize that we actually have 1 over x squared. Now, as we look at this, the derivative of y is dy dx. The derivative of 1 over x is negative 1 over x squared. So if we pull it back together, we get 1 over x times y must be equal to the integral of 1 over x dx. Simplify the right-hand side, and we get the natural log of the absolute value of x plus c. And at this point, we're going to solve for y. So y equals x natural log of the absolute value of x plus c times x. But in our directions, we were told that your x's are always greater than 0, so we don't have to worry about the natural log. And we have y at 1 equals 2. So when we substitute, 2 is equal to 1 natural log of 1 plus c. So c is 2, our final function. Y equals x natural log of x plus 2x. And that is how we use the integrating factor. Let's look at number 3. Is number 3 a first order linear differential equation? I believe it is. And what do we know? We know that p of x is equal to 3, and that q of x is equal to e to the negative x. So our integrating factor, u of x, is equal to e, the integral of our p of x dx, which gives us a nice little e to the 3x. Now we're going to multiply everything by e to the 3x. So we have dy over dx times e to the 3x plus 3y e to the 3x equals e to the 2x once we finish our multiplying. Now check. Here's y. The derivative of y is my dy dx. Here's e to the 3x. The derivative of e to the 3x is 3 e to the 3x. So we are undoing our product rule here. And when we do that, we will get a lovely y times e to the 3x is equal to the integral of e to the 2x dx. Simplify a little bit more, and we will have the right-hand side is 1/2 e to the 2x plus c. Multiply both sides by y. Divide both sides by e to the 3x. Y is going to be equal to 1 over 2 e to the negative x plus c e to the negative 3x. Isn't that beautiful? So I am pretty sure that example 4 is not much different. So I would like you to try this problem on your own. Find your integrating factor to begin with and continue the problem.